March 1946, Huntsville, Alabama. The factory floor does not smell like a laboratory. It smells of oil, steel dust, and heat baked into concrete. Overhead lights hum above rows of identical metal frames, moving forward at a steady pace. Tools hang where hands expect them to be. Gauges flicker, then settle. Nothing here pauses for perfection. A group of German engineers stands silently near the edge of the line. Men who once worked behind guarded fences at Peenemünde. Men trained to treat rockets as instruments of exactness, hand-fitted parts, recalculated tolerances, designs revised endlessly on drafting tables. They had believed such machines could only be built slowly, cautiously, one at a time. But here, rockets advance station by station, not as singular creations, as products. Each unit is slightly imperfect, yet acceptable. Each flaw anticipated, measured, absorbed into a system designed to keep moving. The line does not wait for genius, it waits only for process. For the first time, the shock is not technical, it is philosophical. Because what stands before them is not simply a different way to build rockets, but a different idea of how power itself is manufactured. And that idea did not emerge overnight. It was forged by a war already reshaping the world.
By the time German engineers first glimpsed American rocket facilities, the Second World War had already redefined what industrial warfare meant. The conflict was no longer decided solely by battlefield brilliance or technological novelty. It was being decided by the ability of nations to convert raw materials, labor, and time into sustained military power, without interruption. Germany entered the war with a reputation built on precision. Its industrial culture prized exactness, specialization, and mastery of complex systems. This approach had produced some of the most advanced weapons of the early war years: high-performance aircraft engines, sophisticated optics, and eventually the world's first operational ballistic missile. At Peenemünde on the Baltic coast, engineers were given room to pursue innovation almost in isolation. The V-2 rocket that emerged from this environment was revolutionary. It reached the edge of space. It struck targets at supersonic speed. It could not be intercepted by contemporary defenses. But it was also a product of its culture. Each V-2 required careful hand assembly. Components were often adjusted individually. Subsystems were not standardized across production runs. Changes were introduced continuously, sometimes mid-production, as engineers sought theoretical improvement rather than manufacturing stability. The result was a weapon of remarkable capability and severe fragility as an industrial asset. Production rates remained low. Reliability fluctuated. Every launch demanded extensive preparation, skilled personnel, and time Germany increasingly did not have. By 1943, the strategic situation had turned against the Reich. Allied bombing campaigns targeted factories, transport networks, and fuel supplies. Skilled labor was pulled into military service or lost to air raids. Underground production sites were carved out of mountains, trading safety from bombers for logistical inefficiency. The V-2 program itself was fragmented across multiple facilities, each struggling to maintain quality under conditions of forced labor, material shortages, and constant relocation. At the same time, German military leadership faced a contradiction it could not resolve. The war demanded weapons that could be produced faster than they were destroyed. Yet the engineering culture delivering Germany's most advanced systems resisted simplification. Precision was not merely a technical preference, it was an identity. Engineers were rewarded for innovation, not for throughput. Perfection was pursued as the strategic clock accelerated. Across the Atlantic, the United States was experiencing the war differently. Before December 1941, American industry had already begun mobilizing, supplying Allied nations under Lend-Lease. After Pearl Harbor, that mobilization expanded into something unprecedented. Civilian factories were retooled at speed. Automobile plants produced aircraft engines. Refrigeration manufacturers assembled machine guns. The goal was not elegance, it was continuity. Production lines were designed to function even when individual workers lacked deep technical expertise. Components were standardized to tolerate variation. Design changes were delayed or frozen once production began. This approach was not born of technological inferiority, it was born of scale. American planners understood that modern war consumed materiel at rates no laboratory-driven system could sustain. Aircraft losses numbered in the thousands. Tanks were written off by the hundreds in single campaigns. Ammunition expenditure reached levels that defied pre-war assumptions. Victory depended on replacing losses faster than the enemy could inflict them. Yet rockets posed a unique problem. In the early 1940s, the United States lagged behind Germany in long-range rocket technology. American rocketry was fragmented between military branches, universities, and private contractors. There was no equivalent to Peenemünde, no centralized vision pushing ballistic missile development forward at speed. Rockets were viewed as experimental, not decisive. They did not yet fit the American production model. That hesitation would not last. As intelligence reports detailed German advances and as Allied forces moved closer to Europe, the United States began preparing not just to defeat German rocket weapons, but to absorb the knowledge behind them. The question was no longer whether rockets mattered, it was whether they could be transformed from rare instruments of terror into repeatable tools of power. That transformation required more than captured blueprints. It required a collision between two fundamentally different ways of thinking about machines. And that collision was approaching fast.
By late 1944, the American war economy had reached a level of output unmatched in history. The United States was producing aircraft faster than Germany could replace trained pilots. Shipyards launched Liberty ships in days rather than months. Tank factories delivered vehicles by the tens of thousands. This scale was not accidental. It was the result of a deliberate philosophy. Designs would serve production, not the other way around. That philosophy had limits. Rockets, unlike aircraft or tanks, were unstable systems. They demanded tight tolerances, complex guidance, and materials pushed to their physical limits. Early American attempts to adapt rocketry to mass production struggled precisely because they tried to force laboratory designs onto factory floors without compromise. Failures were frequent. Test programs stalled. Military planners remained cautious. The turning point did not come from a single breakthrough. It came from organizational alignment. As Allied forces advanced into Germany in 1945, specialized intelligence units followed close behind. Their task was not only to seize weapons, but to capture knowledge. Facilities were cataloged. Documentation was collected. Engineers were interrogated, not as prisoners, but as sources of industrial insight. The goal was to understand not just how German rockets worked, but why they were built the way they were. What American analysts discovered was a paradox. Germany possessed superior theoretical designs, yet lacked the industrial architecture to exploit them fully. Production had been treated as an extension of research rather than as a discipline in its own right. Design changes cascaded unpredictably through manufacturing chains. Components were optimized for performance, not repeatability. Quality control relied on skilled oversight rather than statistical process management. American industry approached the problem from the opposite direction. Engineers working under U.S. Army and Navy contracts began breaking rocket systems into discrete modules.
Guidance assemblies, propulsion units, airframes, and control surfaces were redesigned so they could be produced independently, tested separately, and integrated late in the process. Tolerances were widened where physics allowed. Materials were substituted, not for theoretical superiority, but for supply reliability. Documentation was standardized, so a system could be reproduced without the presence of its original designer. This was not an abandonment of precision, it was a redefinition of where precision mattered. Instead of crafting a perfect rocket, the goal became producing many rockets that behaved predictably as a group. Variability was measured, not feared. Failures were tracked statistically, rather than investigated as singular anomalies. A rocket that failed within expected parameters was no longer a scandal, it was data. Captured German engineers encountered this mindset gradually. Some were skeptical, others were openly dismissive. They had been trained to believe that advanced weapons demanded constant human judgment at every stage. Assembly lines, in their experience, were suitable for trucks or artillery shells, not machines that balanced combustion, guidance, and aerodynamics in seconds. Yet the evidence accumulated. American facilities demonstrated that complex systems could be stabilized through process discipline rather than individual mastery. Where German production relied on exceptional engineers, American production relied on systems that assumed average performance and compensated for it. The difference was subtle, but decisive. It allowed expansion without collapse. By 1946, as former German specialists were brought into American programs under controlled conditions, the contrast became unavoidable. They were no longer observing isolated experiments. They were watching rockets treated as industrial units, scheduled, tracked, and delivered on timelines dictated by logistics rather than inspiration. This did not diminish the German contribution. Their theoretical work remained essential, but its role changed. Ideas that once existed only as singular achievements were now filtered through an industrial logic that demanded durability over brilliance. The war had ended, but its industrial lessons were only beginning to take shape. And to understand how deeply those lessons cut, the story must now shift from background forces to the specific angles through which this transformation was experienced.
For the German engineers who entered American programs after the war, the shock was not rooted in defeat, it came from displacement. Many had spent their careers inside tightly controlled research environments where hierarchy flowed from technical authority. The most brilliant designer held influence regardless of rank. Decisions were debated on theoretical grounds. If a calculation demanded revision, production paused. In the United States, that hierarchy was reversed. Engineers found themselves answering to production managers who did not design rockets but understood schedules. Meetings were shorter, debates ended not with equations but with delivery dates. A design that could not be built repeatedly was not refined, it was replaced. For men trained to equate engineering excellence with individual mastery, this was unsettling. Yet the system functioned without them. Assembly workers were trained for tasks, not for understanding entire machines. Knowledge was distributed across documentation rather than personalities. If a specialist left, production did not halt. That continuity challenged a deeply held belief that advanced technology required constant oversight by its creators. The emotional shift was quiet but profound. Engineers accustomed to guarding their work now saw it disassembled into processes others could execute. Their expertise was still valued, but it was no longer singular. It was absorbed into a machine larger than any individual. That realization reframed what it meant to build weapons in the modern world. Angle 2. The technological perspective. German rocketry had been designed to push limits.
Propulsion systems operated near material tolerances. Guidance mechanisms were tuned precisely for specific flight profiles. This achieved unprecedented performance, but it also meant every deviation carried risk. American engineers approached the same problems differently. Instead of optimizing each rocket for peak capability, they optimized systems for predictability. Components were redesigned so slight variations would not cascade into failure. Where German systems demanded precision assembly, American designs demanded tolerance. This allowed parts from different batches, factories, or even different suppliers to function together without recalibration. Testing philosophy shifted accordingly. Rather than perfecting a single prototype, American programs emphasized repeated trials across production runs. Failures were expected early and designed out through iteration, not correction. Once production stabilized, designs were frozen, even if improvements were theoretically possible. Change was treated as disruption. This approach reduced maximum performance, but it increased reliability at scale. The technological shock for German engineers was realizing that superiority could emerge from restraint. The most effective system was not the one that flew highest or fastest, but the one that behaved consistently across hundreds of units. That lesson would reshape how rockets were designed long after the war ended.
From a military standpoint, German rockets had been conceived as strategic weapons. The V-2 was intended to bypass defenses and strike cities directly. Its value lay in terror and novelty rather than battlefield integration. Each launch was a deliberate act, consuming time, resources, and trained crews. American planners evaluated rockets differently. They asked how such weapons could support sustained operations. Could they be deployed repeatedly? Could they be supplied under combat conditions? Could losses be replaced without strategic delay? These questions shifted focus away from individual performance toward operational tempo. Assembly line production made new tactics possible. Rockets no longer needed to be preserved as rare assets. They could be expended. Planning could assume loss. Commanders could factor reliability statistics into operations rather than relying on singular success. This changed rockets from symbols into tools. The tactical implication was subtle but decisive. Weapons designed for repeat use altered how wars could be fought. Firepower became a function of logistics, not ingenuity. Control shifted from the launch site to the supply chain. And once that shift occurred, there was no return to the old model. The remaining angles reveal how this transformation extended beyond the battlefield, into leadership decisions and industrial doctrine that would define the post-war world.
In German rocket facilities, production was often an extension of experimentation. Tooling changed as designs evolved. Workers adjusted components by hand. Quality control relied on inspection rather than process stability. This worked when output was limited and expertise concentrated. American factories operated on a different assumption. Variability was inevitable. Instead of eliminating variation, they contained it. Jigs, fixtures, and gauges ensured parts aligned without manual correction. Statistical sampling replaced exhaustive inspection. A rocket component that met defined tolerances moved forward without debate. The system valued flow over adjustment. This industrial discipline was transferable. Once established, the same production logic could be applied across facilities. A line disrupted by shortages could be restarted elsewhere using identical documentation. Knowledge was embedded into tooling and procedures, not individuals. This made expansion possible without dilution. For German engineers, the realization was stark. Advanced weapons could be industrialized not by simplifying them intellectually, but by restructuring the environment around them. Precision was no longer handcrafted, it was enforced by process. That insight,
permanently altered how large-scale weapons programs would be organized. At the leadership level, the divergence between German and American approaches was intentional. German command structures often granted engineers autonomy, believing technical brilliance could offset strategic disadvantage. Resources were directed toward breakthrough systems even as existing forces deteriorated. Decisions favored innovation under pressure. American leadership favored predictability. Once a system entered production, it was protected from disruption. Even superior alternatives were delayed if they threatened output. The objective was not surprise, it was dominance through continuity. Leaders accepted that incremental improvement, multiplied across thousands of units, outweighed singular advances. This strategic patience proved decisive. When rockets entered American production pipelines, they did so as part of a broader doctrine. Technology must serve strategy, not redefine it mid-conflict. Engineers were constrained deliberately, not out of ignorance, but out of discipline. For those who had worked under a different philosophy, the implication was sobering. Victory did not belong to the most advanced idea. It belonged to the system that could sustain itself under pressure. That truth would soon be tested, not in theory, but in the moment when assembly line rocketry crossed from concept into irreversible reality.
The shift from experimentation to inevitability did not announce itself with ceremony. It unfolded through schedules, shipping manifests, and production charts that revealed a pattern impossible to ignore. In late 1945, American military planners faced a choice. German rocket technology had been secured. Test firings confirmed its potential. The question was no longer whether the United States could build rockets, but how it would build them. Small-scale experimental programs already existed. They could be expanded cautiously, preserving the laboratory-driven model familiar to German engineers. Or they could be integrated into the same industrial framework that had produced bombers, tanks, and ships at unprecedented rates. The decision was made quietly but decisively. Rocket programs were reorganized under production-oriented commands. Responsibilities were divided. Research groups were separated from manufacturing teams. Design authority no longer rested with individuals or isolated centers. It was distributed across committees that included logisticians, procurement officers, and manufacturing engineers. This reorganization altered everything. Specifications were rewritten to favor repeatability. Components were redesigned so they could be manufactured using existing machine tools rather than custom equipment. Materials were selected based on availability and supply stability, not optimal theoretical performance. Changes were locked once production began. Improvements were deferred to future blocks rather than inserted mid-run. German engineers recognized the implications immediately. Under this system, their designs could no longer evolve continuously. Ideas that would have prompted weeks of recalculation were now postponed indefinitely. The rhythm of the factory overruled the rhythm of the drafting table. This was not a temporary compromise, it was structural. Test facilities reflected the same logic. Instead of refining a single rocket through endless trials, American programs fired multiple units built to identical specifications. Failures were logged, categorized, and analyzed statistically. The goal was not to eliminate failure entirely, but to bound it. A system that failed predictably could be planned around. A system that failed unpredictably could not. As production stabilized, numbers began to speak. Output increased not because rockets had become simpler, but because uncertainty had been engineered out of the process. Supply chains synchronized, training programs standardized, documentation replaced oral tradition. A rocket could now be built, tested, and fielded without reliance on its original designer. For German specialists, this moment marked a turning point. Their knowledge was still essential, but it no longer controlled the process. The assembly line had absorbed the science. The broader significance was clear to American leadership.
Once rockets could be produced this way, their role in warfare would expand. They could be planned into operations rather than reserved for exceptional circumstances. Their development cycle could align with strategic timelines rather than scientific curiosity. Yet the transformation was not complete. One final threshold remained, where production scale ceased to be experimental and became institutional. That threshold would be crossed when assembly line rocketry proved it could sustain itself without exception, hesitation, or reversal. That moment was approaching.
The moment assembly line rocketry became irreversible did not occur during a launch. It occurred when the system no longer required explanation. By 1947, American rocket production had crossed a psychological boundary. Facilities were no longer framed as experimental sites. They were budgeted, staffed, and audited as permanent industrial assets. Output forecasts extended years ahead. Training pipelines assumed turnover. Procurement contracts prioritized consistency over innovation. Rockets had entered the same administrative universe as aircraft engines and artillery shells. For German engineers observing this transition, the implications were unmistakable. In their experience, advanced weapons existed in a state of perpetual revision. A breakthrough justified disruption, a flaw demanded immediate correction. Here, flaws were documented and allowed to persist if they did not threaten systemic stability. The system did not bend toward perfection, it bent toward endurance. This endurance reshaped responsibility. Failures were no longer attributed to individuals, they were traced to processes. When a rocket malfunctioned, the response was not disciplinary or corrective in isolation, it was procedural. Data flowed backward through the line, triggering measured adjustments rather than reactive redesigns. The system learned slowly, but it learned reliably. At scale, this learning compounded. As production increased, costs decreased. As costs decreased, procurement expanded. As procurement expanded, planning assumptions changed. Rockets were no longer scarce, they became schedulable. Military doctrine began to treat them as consumable assets rather than strategic novelties. This was the decisive break from the German model. The V-2 had been conceived as a weapon that justified itself through its uniqueness. Its power lay in being unlike anything else on the battlefield. Assembly line rockets justified themselves through sameness. Their power lay in repetition. For American leadership, this realization closed the debate. Once a weapon could be produced predictably, it could be integrated predictably. Once it could be integrated, it could be depended upon. And once it could be depended upon, it reshaped planning at every level: training, logistics, and strategy. German engineers did not dispute the effectiveness of this approach. Many acknowledged it privately. Some embraced it. Others struggled to reconcile it with their professional identity. Years of training had taught them that excellence resided in singular achievement. Now they were confronted with a system where excellence resided in invisibility, where the most successful process was the one no one noticed because it never failed loudly. The assembly line did not celebrate innovation, it absorbed it. By the time these programs matured, there was no path back to bespoke rocketry. The infrastructure had been built, the habits had formed, the logic had proven itself under scrutiny. Rockets were no longer rare expressions of human ingenuity, they were outputs. And with that shift, the future of warfare and technology itself had quietly changed. The war had ended years earlier, but its consequences were now fully alive.
When assembly line rocketry stabilized inside American industry, its immediate effects were subtle rather than spectacular. There were no victory parades for production systems. No single launch marked the transition. Yet within military institutions, the consequences became visible in planning documents, procurement forecasts, and strategic assessments. Rockets were no longer treated as exceptional assets. Budget allocations reflected this shift first. Funding moved away from isolated research programs towards sustained production contracts. Facilities once justified as temporary were absorbed into long-term infrastructure. Training manuals assumed standardized equipment rather than evolving prototypes. The language surrounding rockets changed from experimental to operational. This altered how military planners evaluated risk. Under the German model, each rocket represented a concentration of effort. Losses were costly. Failures were discouraging. Under the American system, loss was expected and accounted for. Reliability was measured statistically across production runs, not emotionally through individual outcomes. This allowed planners to incorporate rockets into broader operational concepts without fear of catastrophic depletion. The industrial consequences extended beyond the weapons themselves. Suppliers adapted to predictable demand. Materials procurement stabilized. Tooling investments amortized over large runs rather than small batches. This created feedback loops that reinforced production discipline. Once established, the system rewarded consistency and penalized deviation. German engineers working within this environment recognized another implication. Innovation had not disappeared, it had been delayed and structured. New ideas were not rejected, but they were scheduled. Improvements were rolled into future variants rather than imposed on active lines. This preserved production integrity while allowing long-term evolution. The contrast with wartime German experience was stark. In Germany, production instability had been exacerbated by constant redesign, bombing disruptions, and resource scarcity. In the United States, even as geopolitical uncertainty grew, industrial planning assumed continuity. This confidence was not ideological, it was empirical, built on years of wartime output. Reports generated during this period reflected a new consensus. Weapons effectiveness was increasingly tied to logistical sustainability. Advanced systems were evaluated not only on performance, but how easily they could be replaced, repaired, and integrated across units. This recalibration affected strategic thinking. Military institutions began to prioritize systems that could scale without loss of control. The lessons drawn were not framed as uniquely American. They were presented as general principles of modern warfare. Control over production was now seen as inseparable from control over the battlefield. Yet the aftermath was not solely institutional. For individuals who had lived through both systems, the change carried personal weight. Engineers accustomed to seeing their work as expressions of intellect now saw it dissolve into documentation and procedures. Success was measured not by recognition, but by absence of disruption. This was not decline, it was transformation. The implications of that transformation would extend far beyond the immediate post-war years into doctrines and industries still forming. To understand how deeply these effects reached, the story must move beyond immediate consequences and examine how this production philosophy reshaped long-term thinking.
As the late 1940s progressed, the effects of assembly line rocketry extended beyond production metrics and into institutional memory. What had begun as a practical solution to wartime pressures hardened into doctrine. Military planners, industrial managers, and policymakers internalized a lesson that no longer needed to be articulated. Technological power was inseparable from the systems that sustained it. This realization reshaped how future programs were conceived. Weapons development cycles were reorganized around phases rather than breakthroughs. Research, testing, production, and deployment were separated deliberately to prevent disruption. Each phase answered to different authorities, ensuring that no single perspective could dominate the entire process. Innovation was encouraged, but contained. This containment altered expectations. Instead of asking how advanced a system could become, planners asked how reliably it could be reproduced under strain. Instead of rewarding novelty, institutions rewarded resilience.
The emphasis shifted from what a weapon could achieve once to what it could achieve repeatedly across time, geography, and organizational change. Cold War planning reflected this shift without fanfare. Documents from the period show increasing concern with sustainment, replacement rates, and industrial depth. Scenarios assumed prolonged competition rather than decisive confrontation. In this environment, the assembly line rocket was not simply a weapon, it was a template. It demonstrated that technological superiority could be preserved through management rather than constant reinvention. German engineers who remained within American programs contributed to this evolution, but not as architects of its philosophy. Their expertise informed design, their experience refined testing. Yet the framework they operated within was no longer theirs. It belonged to institutions that had learned to prioritize continuity over brilliance. This inversion carried consequences for how engineering itself was taught. Training emphasized systems thinking. Documentation became as important as calculation. Success was defined by transferability, the ability of a design to survive its creator's absence. Knowledge was expected to outlive individuals. Over time, this mindset spread beyond rocketry. Other advanced fields adopted similar structures. Aerospace, electronics, and later computing would all reflect the same logic. Innovation mattered, but only if it could be stabilized, replicated, and maintained at scale. The assembly line, once associated with simplicity, had become the backbone of complexity. The aftermath, then, was not a victory measured in numbers alone. It was a reorientation of belief. The idea that technological dominance flowed from singular genius gave way to the understanding that dominance flowed from systems that could endure friction, organizational, material, and human. By the time this lesson was fully absorbed, it no longer felt revolutionary, it felt obvious, which is often how the most consequential changes announce themselves, not with noise, but with permanence. The final question is not what was built on those assembly lines, it is what that method taught the world about power itself.
The assembly line did more than change how rockets were built. It changed how ambition was measured. For generations, technological power had been associated with mastery of materials, of mathematics, of individuals whose insight seemed to lift machines beyond ordinary limits. The war did not erase that mastery, but it placed it inside something larger, quieter, and more enduring. What emerged was a new understanding of strength. Power no longer depended on producing the most extraordinary object. It depended on producing ordinary objects without interruption. Excellence was no longer visible in the finished weapon, but hidden inside the system that ensured the next one would be identical, and the one after that would arrive on time. This shift altered the moral geography of technology. When weapons are rare, their use is deliberate. When they are repeatable, their presence reshapes planning, restraint, and responsibility. Decisions move away from moments and toward processes. Accountability disperses. Outcomes become structural rather than personal. The engineers who once guarded their creations learned that ideas, once absorbed by systems, lose their ownership. They gain reach but surrender identity. What mattered was no longer who designed the rocket, but whether the system could function without asking who had done so. This lesson extended far beyond warfare. It influenced how societies would build, govern, and compete in an age defined by scale. Institutions learned that continuity outlasted brilliance, and that the most powerful technologies were those that could survive routine.
In that sense, the shock experienced by German engineers was not about rockets at all. It was about recognition. They were witnessing the moment when human ingenuity stopped being the center of technological power and became one of its inputs. The assembly line did not diminish innovation, it disciplined it. And in doing so, it quietly redefined what it meant to build the future.